Okay, it's calculus time. Any questions about what we talked about on Monday? Related rates or the beginning of our discussion of Extrema? Okay, so let's review a little bit of section 4.1. And maybe I'll do a couple of the homework problems. So this is section 4.1. Number 11. So, and we want to find the critical numbers of the function f of x equals x cubed minus 3x squared. So there are two kinds of critical numbers. They're points where there is no derivative, it's not defined, it doesn't exist. And points where the derivative f prime of x is 0. So here we have the function x cubed minus 3x squared. F prime of x is 3x squared minus 2x, which is x times 3x minus 2, and that's equal to 0 when x equals 0 and 2/3. So these are the critical numbers. Problem
Why
number,
isn't that -6?
excuse me?
I mean, like the power, like the derivative.
The derivative of
You
x
wrote it
cubed,
wrong up there, like in the question. You wrote -3x to -x to the third minus 3x squared.
Yeah. Oh, I'm sorry. I just copied it down wrong. 3x squared, thank you. So it's 3x squared minus 6x, which is a factor out of 3. It's 3x times x minus 2. And the critical numbers are 0 and 2. Thank you. In number 15, we have the function h of x equals sine squared x plus cosine x. And we're only looking at it on the open interval between 0 and 2 pi. So the derivative of sine squared x is 2 sine x cosine x. And the derivative of cosine x is minus sine x. So this is equal to, well, that's what the derivative is. I can factor out a sine x. I get 2 cosine x minus 1. Or I could, if I wanted, factor out 2 sine x. And then this is cosine x minus a half. In any case, this is equal to 0 when either sine x equals 0 or cosine x equals a half. And sine x equals 0 when x is a multiple of pi. So sine x equals 0 for x in this interval means x is equal to pi. Cosine x equals a half means, so what are the values of the cosine when the cosine is equal to a half? It's equal to pi over 3. And right, remember, this is the graph of the cosine, 0 to pi. It's equal to a half at pi over 3 and 5 pi over 3. So this function has 3 critical numbers in this open interval. Okay. Any questions about this? This is just find the derivative, set the derivative equal to 0, and solve. Let's look at number 23. So we want to locate the absolute extrema on the closed interval from 0 to 4. So the absolute extrema occur either at a critical number or at one of the endpoints on the interval. And the function is g of x equals x squared minus 2x. The derivative is 2x minus 2, and that's equal to 0 when x equal 1. So this is the only critical number, but we have to evaluate the function x, g of x, at the critical number and also at the endpoints. So when x is equal to 0, g of 0 is 0. When x is 1, g of 1 is 1 minus 2 is minus 1. When x is 4, this is 16 minus 8 is 8. So this is the absolute max, and this is the absolute min on this interval. If you look at the graph of this function, at 0, it's 0. At 1, it's minus 1. And at 4, it's 8. Graph of this function. Looks like that. So this point, 4, 8, that's the absolute maximum. And this point, 1, minus 1, is the absolute minimum on this interval. All right, any questions about these? Okay, so again, what you have to know from this section is the definitions. Absolute maximum, absolute minimum, relative maximum, and relative minimum. And for these are extreme points or extrema of the function. You look for the value of the function at the various critical numbers. And with the absolute max and absolute min, you also have to look at the value of the function at the endpoints of the interval if you're on a closed interval. So there's a theoretical result about functions that's very important in applications and in more advanced calculus. Here, I just want to make sure you see what these results are. And there are two theorems. The first is called Rolle's theorem. And Rolle's theorem says the following, that f of x be continuous on the closed interval AB and at every point in the open interval it has a derivative. So to have a derivative means, another way of saying that is the function is differentiable on the open interval from A to B. What is the difference? The open interval from A to B is everything between A and B, but not the endpoints. The closed interval from A to B includes the endpoints. And Rolle's theorem says the following, if f of A equals f of B, that is, the function takes on the same value at the endpoints of the interval, then there is at least one number C in the open interval from A to B where the derivative is 0. And to give you an idea of why this is true, we draw a picture. So here, A and B, and here's the graph of the function. It takes on the same value at A and B. So whatever the function looks like, it starts at this same value and ends at the same value. And the theorem says that somewhere in between, the derivative of the function is 0. So you might say there are two cases. And case 1, which is sort of the trivial case, is the function is constant. It equals some number d for all x in the interval from A to B. So in that case, from A to B, the function is just a horizontal line. This is the graph of y equals f of x, and f prime of x equals 0 for all x. So if the function is constant, it's horizontal. The tangent is a horizontal line, has slope 0. And what about the second case? So the second case is f of x is not a constant function. So if it's not constant, that means there is some x where f of x is different from the value at the endpoints. Let's say there are two cases. It's either bigger than this number, let's call it d. So f of a and f of b have the same value, d. And there's some point in between a and b where the function's not d. It's either bigger than d or less than d. So suppose f of x is greater than d. Okay. There's a relative maximum. So the function has a relative maximum between a and b. That is a continuous function on a closed interval. This is a theorem in calculus or advanced calculus, but we use it here. A continuous function on a closed interval has a maximum value. So there's some point where there's a maximum, say at the point x equals c. But then the derivative at c is 0, because what we proved on Monday is wherever the function has a relative maximum or a relative minimum, the derivative is 0 if it exists. So either the derivative doesn't exist, but we're told the derivative exists everywhere, so the derivative is 0. So that's Rolle's theorem. I mean, basically what it says is, if you have a function y equals f of x on the interval from a to b, and there's some number d, which is the value of the function at a and b. So f of a equals f of b.
Sorry, we can't see.
Oops, thank you. So you have this function y equals f of x defined on the interval from a to b, and it takes the same value at the endpoints a and b. There's some number d, so f of a equals f of b equals d. So this function has a maximum between in this interval and a minimum. If it's not constant, if it has a maximum, then at some point you have this maximum value. Or if there's a minimum, at some point there's a minimum value. And wherever there's a max or a min, the derivative is 0. So that's all Rolle's theorem says. And there's a generalization of Rolle's theorem, which is called the mean value theorem. Which says the following. So it says, so this is the mean value theorem. We have a function f of x. Again, it's continuous on the closed interval from a to b. And it's differentiable on the open interval from a to b. The mean value theorem says there exists a number c in the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. So first of all, notice this implies Rolle's theorem. Because if f of a equals f of b, then f prime at c is f of b minus f of a over b minus a. If f of a equals f of b, this is 0 over b minus a is 0. So in the case when the function takes on the same value at the endpoints of the interval, you get a point c in the open interval where the derivative is 0. And in fact, if you're clever, you can prove this, the mean value theorem, using Rolle's theorem. So the idea is you have a function y equals f of x on the interval from a to b. So this is a, this is b, and this is the graph of the function. And it doesn't take the same value at the endpoints. But what you can do is draw this straight line from this point to this point and define a function which is the difference between f of x and this line. And this difference is 0 here and here, and apply Rolle's theorem, and you will get the mean value theorem. Now let's look at a couple again, in Math 175, it's not the proofs that you're expected to know. It is the really the statement of the results. Let me draw a picture of the mean value theorem. So here's A, here's B. Let's say you have a function that looks like that. So this is the point A, f of A, and this is the point B, f of B. And draw the straight line between those 2 points. So this kind of line is called the secant line. It's just a line joining 2 points on a curve. And what is the slope of the secant line? It's rise over run. You go from height f of A to height f of B. So the rise is f of B minus f of A, and the run is from A to B, which is a distance of B minus A. So the slope of the secant line is this. And the mean value theorem says for some number C in the open interval from A to B, the derivative at C is equal to this. What that says is there's some point C between A and B where if you look at the tangent line, right, here's the point CF of C, and this line is called the tangent line to the curve at this point. The slope of the tangent is the derivative, and this says there's some point between A and B on the curve where the slope of the tangent line equals the slope of the secant line. Or equivalently stated, the tangent line is parallel to the secant line. So geometrically, this is really quite interesting. Let's look at a couple of examples, and I'll choose examples that are in the text. Suppose we take the function f of x equals 5 minus 4 over x. So this is not defined when x is 0. It's defined for x positive and for x negative. What does the graph of this function look like when x is positive? When x is 1, you get 5 minus 4 is 1. When f is 2, you get 5 minus 4 over 2. 5 minus 4 over 2 is 3. So f of 1 is 1. F of 2 is 3. F of 3 is 5 minus 4/3. So that's 3 2/3. Right, this is 15, that's 11/3. F of 4 is 5 minus 4 over 4, which is 5 minus 1, or 4. And in general, this graph is half of a hyperbola. That's the graph of this function, 5 minus 4 over x. And if you look at this, and look at the points 1, 1, and 4, 4 on the curve, this is the secant line. So the slope of the secant line from 1f of 1 to 4f of 4 is 1. 4 minus 1 over 4 minus 1, or 3 over 3 is 1. This line has slope 1. So we know by the mean value theorem there is at least one, maybe more, number c in the open interval between 1 and 4, such that f prime of c is equal to 1. There's going to be some point where the tangent line to the curve is parallel to the secant line. And we want to find c. Well, if f of x is 5 minus 4 over x, or 5 minus 4 x to the minus 1, f prime of x is minus 4 times minus x to the minus 2, or 4 over x squared. And when is that equal to 1? Well, it equals 1 when x squared equals 4, but I'm only looking for values between 1 and 4, so x between 1 and 4, so x equal 2. So at the point x equal 2, f prime, the derivative, so f prime of 2 is equal to 1. So the answer to the problem is x equal 2, or c equal 2. That's the point on this hyperbola between 1 and 4 where the tangent line is parallel to the secant line. So again, this is new material and it takes some time to get used to it and understand it, which means a certain amount of work, but it really is a very nice thing. Here's another problem using the mean value theorem. It explains how you can get a speeding ticket. So this is in section 4.2, example 4. So it says there's a highway and 5 miles apart, there are 2 police cars. So there's a police car here, and 5 miles down the road, there's another police car. And so police car 1, police car 2. And there's a truck moving down the highway. And when it passes this first police car, the truck is going 55 miles per hour. And when it passes the second police car, the truck is going 50 miles an hour. But the police cars not only measure how fast the car is going, but what time it is. And the time it took the car to go this 5 miles is 4 minutes. So the time for the car to go 5 miles is 4 minutes. And the speed limit in this on this road is 55 miles per hour. So the speed limit is 55 miles an hour. this guy, this policeman, the radar says the car is going 55 miles an hour when it passes this car. The radar says he's going 50 miles an hour when he passes the second police car, and still he gets a ticket for speeding. All right. Why does the driver get a speeding ticket? So let's imagine S of t is the position of the car along the highway at time t. So 0, 1, 2, 3, 4. This is time in minutes. And this is distance in miles. And what we know is at time 0, he's at the first police car. At time 4, 4 minutes later, he's at the second police car. And we don't know how he gets, well, he's moving along the highway, so this is certainly increasing. We don't know what his position is as a function of time, but we know this is the starting point and this is the ending point. And we have this line from 0, 0. This is the point 4, 5. At 4 minutes, he's going 5 miles. At 0 minutes, he's going 0 miles. What is the slope of the secant? Well, it's rise over run. 4, 5 minus 0, that's the distance the car traveled, over the time, 4 minus 0. So this is miles, and this is minutes. So he's going 5/4 miles per minute. But we want miles per hour. There's 60 minutes per hour. 4 into 60 goes 15. 5 times 15, 75 miles per hour. That says at some point in the 4 minutes, he's traveling at a speed, the velocity, which is, velocity is S prime of t. At some point, the velocity is going to be 75 miles an hour. To get from here to here in 4 minutes, at some point you're traveling at exactly 75 miles an hour, which means you're speeding, so you get a ticket. Right? My guess is that it's illegal for the state troopers to use mathematics. And if you're going 50 miles an hour, 55 miles here, 55 miles an hour here, and 50 miles an hour here, you can't get a ticket even if you're traveling 100 miles an hour in between. But in any case, in these 4 minutes, the truck definitely exceeded the speed limit. Yeah, for some reason, juries also don't like mathematicians. So I have a friend who was a graduate student in Illinois, and he got called to jury duty. And as they were going through the voir dire, when they were like asking, cross-examining the possible jurors, one of the lawyers said, there's a lot of statistics in this case that we're going to present to the jury. I know you're a mathematician, but when you are evaluating the evidence, you cannot use your knowledge of mathematics. You're only allowed to use common sense. So even if you could analyze the data, they wouldn't let you. It's very interesting. Anyway, that is an application of the mean value theorem. Right? An application, it's very interesting, very nice application. Any questions about this? Maybe I'll do an example just, or an exercise, a homework problem, just to get a problem done. By the way, if you are checking the syllabus, if my calculation is correct, there will be the second exam exactly 3 weeks from today, on Wednesday, April 28th. So I will double check that with the syllabus because we follow the syllabus, and it says lesson 23, exam 2. So that's 6 lessons from now, which is 3 weeks. So it should be correct on the 28th. Okay. So this is in section 4.2. Number 41. We have the function f of x equals minus x squared plus 5. So you know this is a parabola turned upside down. When x is 0, the value is 5. When x is plus or minus 1, the value is 4. When x is plus or minus 2, the value is 1, and so on. So that's the parabola. And find the equation of the secant line joining the points minus 1, 4 and 2, 1. So notice, first of all, just to be sure everything is correct, f of minus 1 is minus 1 squared is minus 1 squared plus 5 is minus 1 plus 5 is 4. So that's this point on the curve, minus 1, 4. F of 2 is minus 2 squared plus 5, which is 5 minus 4, or 1. So this is the point 2, 1 on the curve. And that is the secant line. We want to find the equation of the secant line. So equation of secant line. We know the slope of the line is equal to rise over 1 as you go from 4 to 1. You're going down 3. When you go from minus 1 to 2, you're going across 3. So the slope is minus 1. So the line going through the point 2, 1 with this slope is y equals minus x minus 2 plus 1, which is minus x plus 2 plus 1 is 3 minus x. So that's the slope of the secant line. We want to find a point C between minus 1 and 2, where the tangent line is parallel to the secant line. So we want to find a C between minus 1 and 2, where the derivative at C That means the slope of the tangent at C will be the same as the slope of the secant line, which is -1. So how do we do that? Well, f of x is minus x squared plus 5. F prime of x is minus 2x. And when is minus 2x equal to -1? When x is equal to 1/2. So you let C equal to 1/2. What is f of 1/2? It's minus 1/2 squared plus 5. That's 5 minus 1/4, or 4.75. Right there. And at that point, the tangent line is parallel to the secant line. What are the coordinates of this point? X is 1/2. Y is, let me write this as a fraction, which I prefer, 19/4. 1/2, 19/4. So the equation of the tangent line is y equals the slope. Slope is -1. X minus 1/2 plus 19/4. So y is minus x plus 1/2 plus 19/4 plus 21/4. So this line has slope -1, and when x is 1/2, you get 19/4, just what you're supposed to get. So that is an application, in some sense, of the mean value theorem. Any questions about any of this so far? Okay. So now we come to section 4.3, which is about increasing and decreasing functions. And what is called the first derivative test. So we need to define increasing and decreasing. So we say that a function f is increasing on an interval if for all x1 and x2 in the interval, with x1 less than x2, f of x1 is less than f of x2. So here's x1, here's x2, here's the value at x1, the value at x2 is greater. And this is for any points in the interval. So this really means the function is just getting bigger as you move from left to right. Could go like that, could go like that, but that's increasing. And everything being the same, f is decreasing if whenever x1 is less than x2, that implies that f of x1 is bigger than f of x2. Here, as you move from x1 to x2, the function gets bigger. Here, as you move from x1 to x2, the function gets smaller. And if you want to understand what the graph of a function will look like, it's convenient and very useful, actually, to find the intervals where the function is getting bigger and where it's getting smaller, where it's increasing and where it's decreasing. And the theorem tells us that we get all this information from the first derivative. So we have a function, f of x, and our standard hypothesis is that it's continuous on a closed interval from A to B, and differentiable has a derivative on the open interval from A to B. And the theorem says that if f prime of x is greater than 0 for all x in the open interval from A to B, then f is increasing. If the derivative is negative for all x in the interval from A to B, then f is decreasing. And if the derivative is 0 for all x in the interval from A to B, then f of x is a constant function. The graph is just a horizontal line. So the simplest proof of this comes immediately from the mean value theorem. So the proof uses the mean value theorem. So let's look at the first case. F prime of x greater than 0 for all x in the open interval from A to B. So suppose we have numbers x1 less than x2 between A and B. So by the mean value theorem, there exists a number c between x1 and x2 such that f of x2 minus f of x1 over x2 minus x1 is f prime of c. So f of x2 minus f of x1 is x2 minus x1 times f prime of c. x2 is bigger than x1, so this is positive. And our hypothesis is the derivative is positive. So this is positive. Positive times positive is positive. This is a positive number. So f of x2 is bigger than f of x1. So f is increasing. So this is a very pretty application of the mean value theorem. This quotient is the derivative at a point C between x1 and x2. But if the derivative is always positive, this is positive, which means the numerator is positive, which means the function is increasing. Any questions about this? I mean, this is really a kind of a subtle argument. It's very interesting. And the other two parts are exactly the same. If the derivative were negative everywhere, then this would be negative. That would say that f of x2 was less than f of x1, which means decreasing. And if the derivative were 0 everywhere, this would always be equal to 0. So f of x2 minus f of x1 equals 0 means f of x2 equals f of x1. It means the function takes the same value everywhere. So this is the main result about the first derivative. If the derivative is positive on an interval, the function is increasing. If it's negative, the function is decreasing. So this is a standard type of problem. This is example 1 in this section. Find the open intervals where the function f of x equals x cubed minus 3/2 x squared is increasing or decreasing. Well, what's the derivative? F prime of x is 3x squared minus 3x. 3x squared, derivative of x squared is 2x. 2 over 2 is 1. So this is 3x times x minus 1. What can we say about this? Here's x equals 0. Here's x equal 1. At these 2 points, the derivative is 0. When x is bigger than 1, this is positive. So the function is increasing. So f of x is increasing on the interval from 1 to infinity. Also, when x is less than 0, this is negative, the product is positive. So for x less than 0, f prime of x is still positive because negative times negative is positive, and the function is increasing. So f of x is increasing on the interval from 1 to infinity and on the interval from minus infinity to 0. But between 0 and 1, this is positive, but this is negative. So the derivative is negative, and the function is decreasing. So on the interval 0 to 1, the function is decreasing.
Excuse me, Professor.
Yeah.
I didn't get the second part.
Okay, so let me just go through the whole problem again carefully. So I want to find the open intervals where this function, x cubed minus 3/2 x squared, is increasing or decreasing. And we know by the theorem that the function is increasing on an interval where the derivative is positive, and it's decreasing on an interval where the derivative is negative. So for this function, the derivative is x cubed. So derivative of x cubed minus 3/2 x squared is 3x squared minus 3x, which is 3x times x minus 1. So at x equals 0 and x equals 1, the derivative is 0. When x is bigger than 1, these are both positive numbers. X bigger than 1. So this is positive. The derivative is positive. So when x is bigger than 1, I should write this as an open interval. When x is bigger than 1, the derivative is positive, the function is increasing. When x is negative, less than 0, x is negative, x minus 1 is even more negative. Negative times negative is positive. So when x is less than 0, that means on the open interval from minus infinity to 0, the derivative is also positive, so the function is increasing. But when x is between 0 and 1, x is positive, so 3x is positive, but x is less than 1, so x minus 1 is negative. Positive times negative is negative. So on the interval from 0 to 1, the derivative is negative, and the function is decreasing. So the function is decreasing on the open interval from 0 to 1. All right. Questions about that? So this brings us to the most useful fact, which is something called the first derivative test. So remember, a critical number.
Professor,
Yeah.
like about the interval, why 0 to 1 you open the interval? It's
What do
not
you mean? I don't understand. What do you mean by I open the interval?
like it's supposed to be closing interval, right?
No, no, no. And in fact,
0 and 1 is not include.
the problem says find the open intervals where the function is increasing or decreasing. So on the open interval from 0 to 1, the function is decreasing. On the open interval from 1 to infinity, it's increasing. And in fact, if you look at the graph, it has to look like something like this. This is x equal 1. It's decreasing, and then it's increasing. So you really can't include the number 1 here because, well, I'm not sure. In any case, the book asks you to express it in terms of the open interval. So on this open interval between 0 and 1, the function is decreasing.
So what about at 0? At 0, the function is decreasing or constant?
It's neither. At 0, the function has a relative minimum. But we talk about increasing and decreasing.
But at 0, the whole function is 0.
So you can't talk about, if you want to say a function is increasing at a point, that means there's some interval around the point where the function is increasing or decreasing.
So
if you look at 0, there's no such interval because to the left it's decreasing and to the right it's increasing. There's no interval around this point where it's either always decreasing or always increasing.
Got it.
Okay, so here's what the first derivative says. So let C be a critical number of a function that is continuous on an open interval containing C. If f is differentiable on the interval, except possibly at C, then f of C, it can be classified in the following way. So if the derivative changes from negative to positive, at C. That's what we saw in this picture. Here, C is 0. The derivative here is negative and here is positive. So the derivative changes from negative to positive at C. In that point, you have a relative minimum, which is just what you see in the picture. The slope goes from negative to positive, relative minimum. If the derivative changes from, this is all the same, but changes from positive to negative at the point C. So here's a point. Here the derivative is positive. To the left of this point, to the right it's negative. This means the function is going up and then it's coming down. So you have a relative maximum. And if f prime of x doesn't change sign, then you have neither a relative max or a relative min. So if the sign of the derivative changes at a point, that will tell you you have either a relative maximum or a relative minimum, depending on the direction of the sign change. So the best way to understand the theorem is to start to work examples. So that's what I'll do. So this is example 2. Find the relative extrema. That means relative maxima and relative minima of the function f of x equal 1/2 x minus sine x on the interval from 0, the open interval from 0 to 2 pi. So we have to look for the derivative, find the critical numbers, and look for sign changes. So if f of x is 1/2 x minus cosine x, f prime of x is 1/2 minus the sine of x. Oh, I'm sorry. The function is 1/2 x minus sine x. It's always good to write it down correctly. 1/2 x minus sine x. So the derivative is 1/2 minus cosine x. And that's equal to 0 precisely when cosine x equals 1/2. And between 0 and 2 pi, that occurs at x equal to pi over 3 and x equal to 5 pi over 3. So these are the critical numbers. Those are the numbers where the derivative is 0. So I need to know something about the changes of sign of the derivative around the point pi over 3 and the point 5 pi over 3. So this function, the derivative, is 0 at these 2 points and nowhere else. So in between, it's either always positive or always negative. So I want to look at these three intervals. 0 less than x less than pi over 3. Pi over 3 less than x less than 5 pi over 3. And 5 pi over 3 less than x less than 2 pi. And we know this, it's either always positive or always negative in these intervals. So I can just pick a test value, some number in between, to test what the function is. So again, this is the derivative. Suppose for my test value, between 0 and pi over 3, I'll pick pi over 4. Between pi over 3 and 5 pi over 3, I'll pick pi. Between 5 pi over 3 and 2 pi, I'll pick 7 pi over 4. So what is the sign of the derivative? So f prime of pi over 4 is a half minus the cosine of pi over 4. That's a half minus cosine of pi over 4, 1 over root 2. So this is 1 minus root 2 over 2, which is negative. So here, the sign f prime at pi over 4 is negative. What about pi? What's f prime of pi? Well, cosine of pi is minus 1. So this is a half minus minus 1. That's 3 halves, which is positive. And what about 7 pi over 4? F prime of 7 pi over 4 is a half minus cosine of 7 pi over 4. Cosine of 7 pi over 4, that's this angle, is minus 1 over root 2. So is 1 over root 2 also. This is a half minus 1 over root 2, which is also negative. So on this interval, the derivative is always negative. So I'll just write it up here. Here the function is decreasing. Here the derivative is positive, so the function is increasing. Here the derivative is negative. The function is decreasing again. Okay. I'll do 1 or 2 more problems and then we'll be done for today. So this is example 3. Find the relative extrema of the function f of x equals x squared minus 4 to the power 2/3. So we need to look at the derivative and find the intervals where the derivative is positive or negative. So what is the derivative? By the chain rule, this is 2/3 x squared minus 4 to the minus 1/3 times the derivative of x squared minus 4, which is 2x. So this is equal to 4x over 3 times the cube root of x squared minus 4. So f prime of x equals 0 precisely when x is 0. And f prime of x does not exist when x squared minus 4 is 0, when x is plus or minus 2. So we have critical numbers at minus 2, 0, and plus 2. So I have to look at the value, the sign of the derivative on the intervals from minus infinity to minus 2, from minus 2 to 0, from 0 to 2, and for x bigger than 2. And in each of these intervals, I pick a test value. So here I could pick minus 3. It's my test value. Here I could pick 1. Sorry, minus 1. Here I could pick plus 1. And here I could put 3. And what is the sign of the derivative in these three intervals? So f prime of minus 3, this is the derivative, it's 4 times minus 3 over 3 times the cube root. What is minus 3 cubed? Minus 3 times minus 3 is 9. 9 times, I'm sorry, that's the cube root, this is x squared. So this is 9 minus 3 squared minus 4 over 5. This is negative, this is a positive number, and this is negative. So here the sign is less than 0. What is f prime of minus 1? It's 4 times minus 1 over 3 times the cube root of 1 minus 3. That's minus 3. The cube root of a negative number is a negative number. So we have a negative number in the denominator, but also in the numerator. So the quotient is positive. So I should say in this interval, the function is decreasing. Here it's increasing. What about when x is 1? F prime of 1 is 4 over 3 times the cube root of 1 minus 4 is minus 3. This is negative times positive. This is negative, so we have a decreasing function. And f of 3 is 12 over 3 times the cube root of 5 is positive. So this is increasing. So on this interval, the function is decreasing. Here it's increasing. Here it's decreasing. Here it's increasing again. Okay. Any questions about this?
So you mean here we have 2 max and 2 mins?
Sorry?
You mean we have 2 max and 2 min here?
No, no, no. There's no maximum. I haven't discussed maximum or minimum at all. I'm only discussing where the function is increasing and decreasing. I don't know where we have a maximum or a min. Well, actually I do, but it's because there's only, well, but I didn't work that out. The problem asks for the intervals where the function is increasing and decreasing.
So you will use this example to find the minimum and maximum, right?
Well, yes, because I know it's decreasing and increasing, decreasing and increasing.
Right.
That's true. But I'm just trying to answer the problem that's being asked. But
Okay.
what you said is exactly correct.
Thank you.
All right. There's suddenly a huge amount of noise here. So in any case, we've covered everything that I wanted to cover today and a bit more actually. So we will stop for the day and